We're recording now. All right, so we were last time we started the finding the z inverse. Given the z, we discovered the recover the real sequence. And there are different methods, and we're gonna continue with that. And so there is a method called long division. So this is long division. So let's say we want to have, this is example 3.17. Let's say we have AZ equal to Z over Z squared minus 3Z plus 2. All right. So we're going to write this as 3Z squared, Z squared minus 3Z plus 2. And then we're going to have Z here. And now we need something to multiply Z squared with, will give us Z. So that will be Z to power negative 1. So you multiply this stuff here, you will get Z minus 3 plus 2Z minus 1. You subtract and you get minus 2Z minus 1 plus 3. So now something to cancel the 3 is going to be minus 3, okay, plus 3Z minus 2. This is Z minus 2. And you multiply, that will be 3 minus 3Z minus 1 plus 2Z minus 2. No, minus 9 plus 6. And then you add this go away with that one. You see? So we have minus, this will be plus, will be 7, Z minus 1, minus so we would have, as I said, plus 3 or plus 2Z minus. So we're multiplying by plus. Plus 6. And then you have minus 7, Z minus 1. The 3 go away, and minus 6, Z minus 2. Then you want to try to get rid of this. You multiply by 7, Z minus 3. 7Z minus 3 will be, because you need to get rid of this. So that will be 7Z minus 1 minus 1Z minus 2 plus 14 Z minus 3. Okay? And so you multiply by minus, and if you multiply by minus here, minus, a plus, minus, and then you add them. So you're going to have 21. So you're going to have 15 Z minus 2 minus 14z minus 3, and you continue that way. So this is z minus 1, okay, plus 3z minus 2, plus 7 z minus 3, and you continue all the way, and if you, so you're going to have a plus, you will continue with that. And so here, what would that be if you want to cancel out this, the 15? That will be plus 15 z minus 2, z minus 4. Okay, z minus 4. And then this and that one will cancel out. If you multiply by 15, z minus 4 times z squared, this will cancel out, and then you will see what you have. So this is equal to n equals 0 to infinity 2 to the n minus 1 z to power minus n. And so an is 2 to the power n minus 1. Okay? Now you could have done this by partial fraction, but we have not talked about it yet. We will in a second. All right? Okay. Any questions? So this is a long division, really. You just continue with this. It goes on and on and on and on. Okay? All right. Oh, I should erase my board last time. All right. So now we're going to do partial fraction. So this is similar to what you know. So find an when az is 2z squared plus 3z over 2z minus 1 times z plus 1. Okay? Now, you know, these are of the same power. So I am going to rewrite this as, so this is going to be rewritten as az over z equal 2z plus 3 over 2z minus 1 z plus 1. Okay? You will see why we have to be, but because z is common and the power are the same, so that's usually partial fraction works better when the numerator has a higher degree than, sorry, when the denominator has a higher degree than the numerator. So what we're gonna do is we're gonna write 2z plus 3 over 2z minus 1 z plus 1 as f over 2z minus 1 plus b over z plus 1. Why did I start with f? I didn't want to use a because this a is not the same as this a if I use it. Okay? And then I take common denominator. That is f times z plus 1 plus b times 2z minus 1 over 2z minus 1 z plus 1. Okay. And so equating both sides, or 2z plus 3 equal f z plus 1 plus b 2z minus 1, or 2z plus 3 equal to, if I factor z out, I'm gonna get f plus 2b z plus f minus b. And so f plus 2b equal to 2 and f minus b equal 3. Okay? If I multiply by minus f plus minus and add, I'll have 3b equal minus 1, or b is minus 1/3. Then if I have, then f is 2 minus 2b, that is 2 plus 2/3, that is 6, that is 8/3. Okay? So that is a f and b. All right? And so hence a az over z equal to f, and f is 8/3 over 2z minus 1 minus b 1/3 over z plus 1. Or that implies an is 8/3 z inverse. I'm going to multiply by z of z over 2z minus 1 minus 1/3 z inverse of z over z plus 1. You see, I needed z in order to have one of those basic identity. Okay? And that is equal to 8/3 times 1/2 z inverse over z minus 1/2. You see, I factored 2 out in the bottom. And minus 1/3 z inverse z over z minus 1. So that is 4/3. What is that here? Is 1/2 to power n. Remember that? Minus 1/3. And times. Okay? Okay, there is a typo. We need to be careful. I don't know how they did that. Okay, so this is what the answer looks like. Okay. And if you're looking at that will be z bigger than 1. So this actually valid for z bigger than 1, and then you will see the z inverse. Okay. Any questions? Okay. Well, why do we use the z transform? Well, we use it to solve some equation. So this is example 3.19. This is delay switch. Let's consider the nth order xn plus 1 plus xn equal to gn x0 equals 0, and gn is 2 to power n for 0 less or equal to n less or equal to k minus 1, and 0 for n bigger or equal to k. So basically, we're gonna solve. So the question is find xn. Okay. So first of all, your gn is 2 to power n minus 2 to power n u of nk. Why? You see, this one is 0 for n less or equal to k minus 1. So this is 0 for n less or equal to k minus 1. So you'll have 2n minus 0 will get 2 to the n. Now for n bigger or equal to k, that is 1. So you get 2 to power n minus 2 to power n, you get 0. Okay? So see definition 3.3.1 for that. Okay? So we're gonna let x of z equal z of x of n. Okay? Then we'll have z plus 1 x of z equal to the z transform, the z inverse of 2 to the n minus the 2 to the n u k n k. Okay? I mean, you apply because you have x0 equal to 0. So that's what you're gonna get. This here will give you that. Because x0 equals 0, xn plus 1, the z transform of it is zxz, and this one is xz. Okay? All right. Now, what is z 2 to the n u n k? That is z to the n minus k plus k u n k, and that is 2k z of 2 to the n minus k u n k, and that is 2 to the k times z1 minus k over z minus 2. Okay, C theorem 3.35. Okay, for that, we did it. Okay, why did I multiply? Why did I add minus k plus k? Because I know a formula of z of u to the n minus k, a n minus k of that, and that is equal to that. Okay. All right. So now, what do we have now? So all right, so I'm gonna have, hence, we have z plus 1 x z equal to z over z minus 2 minus 2k zk minus 1 or 1 minus k over z minus 2 divide by z plus 1, and then we'll get xz equal to 1 minus 2k z minus k times z over z plus 1 z minus 2. Okay. And I'm gonna split this into 2, z over z plus 1 z minus 2 minus 2 to the k z minus k z over z plus 1 z minus 2. Okay. So now we're gonna do partial fraction. We're gonna do, so we need to find constant alpha, alpha, beta, gamma, and delta, such that this is a really weird partial fraction, such that alpha z over z minus 2 plus beta z over z plus 1 plus gamma z minus k z over z minus 2 plus delta z minus k z over z plus 1 is equal to is equal to 1 minus 2k z minus k z over z plus 1 z plus 2. All right, so I am simplifying by z on all sides, So take the common denominator. And setting numerators equal, we get alpha z plus 1, okay, plus beta z minus 2, plus gamma z minus k, z plus 1, plus delta z minus k, z minus 2, equal to 1 minus 2k z minus k. So you take a common denominator, and this z that is common here, here, here will simplify with that. So if you take common denominator, you're gonna have alpha z plus 1, plus beta z minus 2, plus gamma z minus times z plus 1, because z plus 1 is missing, plus delta z minus k, z minus 2, equal to 1 minus 2 to the k, z minus k. Now equate coefficient on both sides. So you're gonna do, so the z will be 0, the coefficient of the z will be 0, the constant will be 1. So with that in mind, so you're gonna have, if you factor z out, you have alpha plus beta, and that's it. Alpha plus beta z plus alpha minus 2 beta, and that's it. Plus okay, so we're gonna have and let's take a concentrate on gamma plus gamma plus delta z minus k, okay? No, gamma minus 2 delta. Gamma minus 2 delta. All right, so this is what we're gonna have. So and that is, if you factor it, so this is gonna be alpha plus beta is gonna be 1, because it's times alpha plus beta is 0, alpha minus 2 beta is alpha minus 2 beta, this is constant, equal to 1, and gamma minus 2 delta, gamma minus 2 delta, okay, equal to minus 2, okay? And we have one more, gamma plus delta, and we have gamma plus delta equals 0. Okay, so we have all that. So why, where is this gamma plus delta equals 0? You see, you're gonna have a plus gamma plus delta z minus k plus 1. And all that is equal to 1 minus 2k z minus k. You see? Okay. Gamma minus 2k, that is minus 2 to power k, sorry. Okay. All right. And so what we are going to get is this equation will give us alpha is 1/3, beta is minus 1/3, gamma is minus 1/3, 2 to power k, and delta is 1/3, 2 to power k. That's what we're gonna get. Okay. All right, so now we need to compute the Z transform. So what do we have here? All right. So now XZ, we wrote XZ as the transform. So now we need to find the inverse of alpha Z over Z minus 2. And that is 1/3 times 2 to power n. I need the inverse beta Z over Z plus 1. And that is minus 1/3 times minus 1 to power n. Okay. And I have the inverse of gamma Z minus k, Z over Z minus 2, that is minus 2k over 3 gamma Z inverse of Z 1 minus k over Z minus 2, and that is minus 1/3 2 to power k and times 2 to power n minus k. Okay. And you can simplify the k, that's fine. And we have last one, the inverse of delta Z minus k, Z over Z plus 1, that is 1/3 2 to power k minus 1 n minus k. Okay. And then you have the solution. So you notice what we did. Gn is 0. Okay. You notice what we did. Gn is 0 for n bigger or equal to k. But then we're gonna write this is for n bigger or equal to k, and we're gonna have, you can see what we are going to have is, now you write the solution in terms of two parts. It's gonna be 1/3 2 to the n minus 1/3 minus 1 to the n for n less or equal to k minus 1, and then 1/3 2 to the n minus 1/3 minus 1 to the n minus 1/3 2 to the k 2 to the n minus k plus 1/3 2 to the k minus 1 to the power n minus k for n bigger or equal to k. Okay? So these are the two solutions what we're gonna have. All right. That is a long and then you can do a second order differential difference equation. So let me do one. I'm gonna skip one example and I'm gonna do second order. All right, solve xn plus 2 plus xn equal 1, x0 equal x1 equal 0. So again, if we let xz is z of xn, then this becomes xz over z equals z over z minus 1 z squared plus 1. Okay? If we write it like this. Do you remember? You're going to use the theorem. There is a corollary that we did of the z transform of xn plus 2, xn plus 3, and so forth. So we're going to do partial fraction. So that is equal to a over z minus 1 plus bz plus c over z squared plus 1. Okay? Any questions? All right, if I do that, then you take the common denominator, you'll get a equal 1/2, b equals c equal minus 1/2. You just take the common denominator. See, this is equal to a over z squared plus 1 plus bz plus c times z minus 1 over z minus 1 z squared plus 1. Okay? So All right. So now we have xn is the inverse of, I mean, we're gonna divide by z. So we have is z, okay, times a over z minus 1 plus bz plus c over z squared plus 1. Okay. And that is 1/2 z inverse z over z minus 1 minus z inverse of z squared over z squared plus 1, and then minus z over minus z inverse over z squared plus 1. And the 1/2 I took it out. Now what is this? This is 1/2 of the z inverse of that is 1 minus the z inverse of that is cosine n pi over 2. And this one is minus sine n pi over 2. Okay. All right. Well, you can use this one. You can do this one without the Z transform, of course. What you can look at lambda square plus lambda equals 0, right? And you're gonna get lambda square plus 1 equals 0. So you're gonna get lambda equal plus or minus I. So this is for the homogeneous solution, XH. And now XP is some number A, turn out to be 1/2. You see that? So you use the tangent to use what we have used before, and you will get the same answer. Okay? And Z transform gave us the same answer. Okay, let's take a 5 minutes break and come back for this. All right? I'm gonna do system, and then I'm gonna move on to some convolution. And then I'm gonna be done with the Z transform and move on to chapter 4 and 5. Okay, let's take 5 minutes break. expression. I don't know what that means. Doesn't mean much. I don't know. Okay, I'm back. Okay, now we're gonna do system. So this is example 3.12. System. So basically, find xn and yn for xn plus 1 minus 10 yn minus 7 xn equal 0, yn plus 1 minus 4 yn minus xn equals 0. We have x of 0 is a 3, and we have y of 0 is 2. Okay. So we're gonna let x of z equals z of xn. Y of z is z of yn. Okay. And then apply the transform to both sides. Okay. Apply the transform to both sides. And after some simplification, we get z minus 7xz minus 10yz minus 3z equals 0, and minus xz plus z minus 4 yz minus 2z equals 0. Okay. So the best way is we need to eliminate one of the either xz or yz. I think it will be easier to multiply this equation by z minus 7 and then add the equation. So if I multiply this equation by z minus 7, this will be 0, and then this will be minus 10 yz plus z minus 4 z minus 7 yz okay? And minus, I'm multiplying by z minus 7 minus 2z, z minus 7 minus 3z equals 0. Okay? Oh, z minus 4, this is minus 4. Z minus. Did you see what happened here? So if I keep these together, if I multiply by yz, this is gonna be minus 10 plus z squared minus 4z and minus 7z minus 11z, and then plus 28 equal to, now equal to 2z squared. If I take this over there, and then I have plus 14z minus 3z plus 11z, so it will be minus 11z. See what I did? So I'll have yz times z squared minus 11z plus 28 minus 10 plus 18 equal to z of 2z squared minus 11. Okay? Now, I'm gonna get rid of this. Okay? Oh, sorry. That's z minus 2z minus 11. Now this factor into z minus 2, z minus 9. Yeah. So this is yz of z minus 2, z minus 9 equal to z2z minus 11, or yz over z equal to 2z minus 11 over z minus 2, z minus 9. Okay? Okay? So that's gonna be a over z minus 9 plus b over z minus 2. We're gonna do partial fraction. You're doing this as a partial fraction. All right? And so we are gonna end up with a equal 1, b equal 1. So this means a equal b equal 1. After you do a common denominator and you do the calculation and you set it equal to tz minus 11. Hence, yz over z is 1 over z minus 9 plus 1 over z minus 2, or yz is z over z minus 9 plus z over z minus 2. And therefore, yn is z inverse of yz, and that is 9 to power n plus 2 to power n. Okay? All right, so now we have yn. We need xn. Well, that's easy now. Really. So use this one. So xn is yn plus 1 minus 4yn. That is 9 to power n plus 1 plus 2 to power n minus 4 9 to power n minus 4 2 to power n. There you go. Okay. Now we can simplify this a little bit. Okay. So this becomes 5 times 9 to the n minus 2 to power n plus 1. Okay. Now, suppose you use this one. If you use this one, so we ended up using this one here. We use this one to find xn, but if you use this one, you're gonna have to do xn plus 1 minus 7xn equal 10yn, and that is equal to 10 times 9 to power n plus 10 times 2 to power n. Then you're gonna have to solve this equation here. You see, this is the first order now. But here, all we needed to do is compute yn plus 1 because we know yn. Here it's the other way around. What are you talking to? Hannah, I thought talk about the car. All right, any questions? Okay, so that is this one. Oh yeah. Now we're gonna do residue or inverse integral. Okay. Now, the residue method is deeply rooted in complex integration because z here is a complex variable. So I'm gonna wave my hand through some complex theory, but I decided to put it in the book without any reference to complex analysis because this topic is very important. So let's take a look here. Definition 3.5.2. If g of z is a complex valued function given by g of z equal to gz over z minus 0 to power k, where g of z naught is not 0, then g of z is said to have, ideally, did you get hot? To have a pole at z naught of order k. So the order of the pole is k. Now, if k is 1, then the pole z naught is said to be simple. Okay? All right? Okay. This is a very important theorem. This is called theorem of the residue. Let z of an equal az. If az has a pole at z naught of order k equal 1, 2, and so forth, then the residue alpha k is given by, I don't want to miss this one out. Can you see it? Alpha k is equal to 1 over k minus 1 factorial, and the limb as z approaches the pole z naught, and that is the derivative of k inverse k minus 1 over d zk minus 1 of az times z minus z naught to power k times zn minus 1. There. We're going to do a couple examples, and all right. I mean, I will do a complete example in a second, so let me finish those. So basically, for like alpha 1 will be no derivative. If k equal 1, like here, if k equal 1, then there will be no derivative here, will be only the function, so will be the limit, will be 1 over 0 factorial, that is 1. Limit as z approaches z naught will be az, forget about the derivative because the derivative becomes the function, nothing else. times z minus z naught to power 1 times z n minus 1. Okay, so that is the alpha k. And Lily is here to say hi. I think she got outside with mommy and she got very hot. Did you get hot? All right. So let's do a theorem now, and then we will do an example. All right. Theorem 3.5.2. Let z of an equal az. Let C be a closed contour, it's a curve that is a closed curve that contain all isolated singularity singularities of AZ. That means all the Z naught. Then AN, this is the sequence that we're trying to do the Z inverse of, is 1 over 2 pi I, the integral, the line integral of AZ times Zn minus 1 dz, and that is the sum of the residue of AZ. Sum of residues of AZ. Okay? Forget about this one. This is from complex analysis. Okay? We're not going to talk about this, but it's a result worth mentioning without much proof. Just basically, we waved our hands. All right? All right. So find an of az equal to 2z squared over z minus 2, z minus 4, and z bigger than 4. I mean, you may do this one by partial fraction, but let us see how we use the z inverse, the singularity. So what is alpha 1? Alpha 1, so we have this function, we have two residues, z0. So we have 2 and 4. All right, so alpha 1 is, remember what are the alphas? Alpha k, okay? So alpha 1 is lim as z approaches 2 of z minus 2 times 2z squared over z minus 2, z minus 4, zn minus 1. Look, write it down and let's flip the board. Remember, this is z minus z naught, that is az, and that is zn minus 1. Let's flip. Look at it. 1 over
Wait,
k
Professor,
minus,
could you go back?
like here.
Yeah, hold on.
So basically here, so here we have k equal 1. K equal 1 for both 2 and 4, because it's a simple. These are simple poles. All right. So let's take a look. K is 1, so alpha 1 is 1 over 0 factorial 1. Z approaches 2. K equal 1, that will be no derivative, will be az, z minus 2, zn minus 1. You see it? Z minus 2, az, zn minus 1. All right. So now this and this simplifies. So you are having the limb as z approaches 2z squared over z minus 4 times 2 to power n minus 1 times z to power n minus 1. So take 2 equal to 2. So that is 4 over minus 2 times 2 to power n minus 1. And that is minus 2 times 2 to power n minus 1. Okay.
Professor, would that be 8 on the numerator?
8.
It's 2 times z squared.
What did I say? Oh, yeah, 8. 8. Okay. So that is minus 4. All right. Okay. And you can simplify this as minus 2 squared times 2 to the n minus 1, and that is minus 2 to power n plus 1. Okay. So alpha 1 is minus 2 to power n plus 1. Okay. What is alpha 2 now? Alpha 1, alpha 2 is, we're going to look at, remember, we're looking at z minus z0 to power 1. All right. So alpha I, okay. So this is alpha, okay. I made a mistake here. This is alpha I. Let's see. I mean, the k is then the residue alpha k. So based on, so is the sum of the residue. So we need to distinguish between. We need to distinguish between I. You see, alpha I. Here, I is 1 and 2. This is the number of the poles. K is the multiplicity of the pole, correct? So I is 1 and 2 here. Okay, so if I do that, that's what I'll get. Now for alpha 2 is going to be the same. It's going to be z minus 4 2z squared over z minus 2, z minus 4, zn minus 1. And now as limit approaches 4 now, and then this one over this one will cancel, and you are left with lim as z approaches 4. That would be 2z squared over z minus 2 times zn minus 1. Is that good? So that is 2 times 16 over 2 times zn minus 1. Sorry, 4n minus 1. Correct? And that is 13. So that is 4 to power n plus 1. So now, finally, an is alpha 1 plus alpha 2. And what is alpha 1? Alpha 1 was minus 2 to power n plus 1 plus 4 to power n plus 1. There we go. We got it. Okay. So this is very simple. I mean, some if you have AZ, you may be able to apply multiple methods. And the partial fraction is the most powerful one that can apply to many different situations. Okay. Let's do one more example and I will stop.
Hey, Professor, I do have a question.
Yeah.
Using the formula for alpha sub k, it was just chance that like we only went up to k equals 2, so the 1 over k minus 1 factorial was just 1 for both of them. But normally, like
no,
if you have,
I mean, this alpha k, I abuse notation. Okay, it should be like a different index. You know what I mean? Okay.
so it's a different k than what we are using for subscript.
Yeah. Basically, the alpha 1, alpha 2, alpha I. So basically, the alpha depends on this and this. How many poles do we have? 2 poles, right?
Yeah.
So basically, we have 2 poles. So we have alpha 1, alpha 2, and k equal 1 for both. You see what I mean?
Yeah, k is the multiplicity of the pole.
Yes.
Okay, different k. All right, I got you.
Okay. I did abuse notation. I can see. All right.
Yeah, I'm good.
Yeah. So let's say we have over z minus 5, then you will have alpha 1, alpha 2, alpha 3, and k still 1 for all of them. Okay? How's that? Now the next example should make it clearer. Let's do one more example. Now let's say we have AZ is z over z minus 2 cube and z bigger than 2. So here what we have is z0 is 2 and k is 3, correct? And there is only one alpha, only one alpha. Say alpha 1. Okay, how's that? All right, so we're gonna do alpha 1 is 1 over 2 factorial, the second derivative, okay, of z over z minus 2 cube times z minus 2, zn minus 1. See what happened here? And this is the limit. Sorry, I have limit. Z approaches to it. Okay? Now, this is 1 over 2 factorial. Let's simplify this. The lim as z approaches 2. Okay? The theorem says, let's see what the theorem says. Oh, z minus 0 to power k. Sorry, this is a cube. Okay? Look at the theorem. So this cancels out, and that becomes Zn. So you're taking the second derivative of Zn. So this is 1 over 2 factorial, the lim as z approaches 2 of n times n minus 1 times zn minus 2. And that is 1/2 times n minus 1 times 2 to power n minus 2. And that is n times n minus 1, 2 to power n minus 3. Okay? So the an is alpha 1, which is n times n minus 1 times 2n minus 3. That would have been difficult to do it by any other means. You see what happened here? All right. I think I'm gonna stop here, and gonna stop the AI thing. And stay online if you like. I want to say something, but I'm gonna stop recording.